Hey guys, in this video we're going to discuss about the idea behind the first principles of differentiation and how it came about in a very simplistic approach. On a side note, if you haven't learned the lesson functions already, I highly recommend that you do so before watching this video, especially the linear functions aka straight line graphs. Having said that, let's start with a quick recap at straight line graphs. We know that any straight line graph can be written in the format of y equals mx plus c, where m is the gradient and c is the y-intercept. For example, let's have a look at the graph y equal 2x plus 3. Y equals 2x plus 3. So it's very clear that the gradient of this graph is 2. The gradient is 2. Now what does that mean? Well, it means that the rate of change of y compared to x is 2. In other words, if you were to increase x by 1 unit, y will increase by 2 units. For example, if I take 2 points on this graph, let's say x equals 1, y equals 5, and then x equals 2, y equals 7. Now if you see here, when x increased by 1 unit, from 1 to 2, y increased by 2 units. 2 units. When x increased by 1 unit, y increased by 2 units. That is what is meant by the gradient. The gradient tells you how much y moves as you move x by 1 unit. Now let's try and generalize this idea. So I can say that this point is x1 and this point is x2 and this point is y1 and y2. Now as we all already know, the way to find the gradient is that you divide the rise over run. So gradient equals rise over run, which means the change in y divided by the change in x. The change in y would be y2 minus y1. The change in x would be x2 minus x1. Now this is not something new, this is something that we've already learned in our younger grades, and we know how to find the gradient of any straight line graph by using this formula. However, the problem now is to find the gradient of a graph that is curved, that is not really a straight line. Now when the graph is curved, we are not able to do the same thing like we did for a straight line graph. Let's have a look at a curved graph. Now let's take this curve as an example. Let's take a point x1 here and then x2 here. By looking at the curved nature of this graph, we understand that the slope is not constant and keeps increasing as we move in the positive x direction. If you look at the slope at x1, it's less steeper compared to the slope at x2. So the slope keeps increasing and therefore you will not be able to apply the same formula as you applied for a straight line graph. So the problem here is that a curve does not have a constant increment. It is not a straight line. So to solve this increasing slope issue, we can zoom into the graph. And by zooming into the graph, what I really mean is that we try to look at the graph at a very smaller scale. Like we can make the axis into 100th or 1,000th of the current scale size. And what that would really mean is that the change in x that you're taking is a very small change. So what difference does it make if you go for a very smaller scale? Well, let's have a look. So let me explain to you what I meant by zooming in to the curve graph. So when I zoom into the curve graph, you see the scales are getting smaller. Now it's come to the first decimal place and I'm zooming in further, and now the scales have gone to the second decimal place. I'm zooming in further, the third decimal place, and you can notice now that the curve graph does not appear to be a curve graph anymore. It now looks like a straight line graph. It has the nature of a straight line graph. So when we zoom in and when we go to a smaller scale, we understand that a curve graph appears to be a straight line graph. So this makes us think, maybe if we zoom in enough so that the curve graph becomes a straight line graph, then we'll be able to apply the straight line gradient formula. So let's do that. So this is our initial curve graph that we drew. So let's try and zoom in further. Alright, so you see at this point it almost looks like a straight line graph where we'll be able to apply the same straight line formulas that we applied earlier. So I'm going to name this point as my x1 and this point as my x2. And therefore this height over here, this point will be y2 and this point will be y1. So if we apply the same formula again, we know that the gradient is equals to y2 minus y1 over x2 minus x1. So now by zooming into a curve graph, we've actually made it look like a straight line graph, and therefore we were able to apply the same straight line graph formula. So that's it, we are now able to get the gradient of a curve graph by using the straight line equation. So now that we have our formula, we're going to change the notations a little bit to make it look well defined. So instead of saying x2, we're going to go ahead and call this point as x1 plus h. This is just to indicate that we've moved x by an amount h. And from the lessons functions, we know that y1 can be written as f of x1, as x1 is the input, and y2 can be written as f of x1 plus h, because at this point we just changed the input to be x1 plus h. Now all we have to do is just go ahead and change the formula accordingly. So now we can say that gradient is equals to rise over run, which is the change in y over the change in x, right? We write that by delta y over delta x. That triangle is read as delta. So that is the change in y over change in x, and that the formula we know is y2 minus y1 over x2 minus x1. However, since we've changed around the notations a little bit, let's go ahead and write in that notation. So y2 is considered as f of x1 plus h, y1 is considered as f of x1, and this gets divided by x1 plus h minus x1, and x1 plus h minus x1 is just h. So this can be written as f of x1 plus h minus f of x1 divided by h. Now we have to change one more thing, and that is this delta y over delta x. As a notation, usually delta y over delta x talks about a considerably larger change of y divided by a larger change of x. However, in this case, since we've zoomed in too much and we went into a very smaller scale, this change isn't as big. This change is only a change in 100th of a decimal or 1,000th of a decimal, and therefore we would not be using the same triangle notation anymore, because as I mentioned earlier, triangle notation are most often used when the changes are considerably larger. And therefore, instead of saying difference of y divided by difference of x, instead of putting the triangle there, we'll now put the letter d. So d, difference in y divided by difference in x. Now this is the formula of first principles. However, we just miss one more thing, and that is just the notation that tells that h is very small. So how do we tell that? We tell that using the notation of limits. So we say limit h tends to 0 and dy by dx equals f of x1 plus h minus f of x1 divided by h. What we are really saying here is that we are saying that h is very small. Remember that we have to mention that we zoomed in. So how do we say that in an equation? It's by saying that h is very close to 0. That's what the limit notation says. It says limit of h tends to 0. That means the change of h here, the change that we made here, is so small, that is so close to 0. And with that, we arrive at the first principles of differentiation. We know dy by dx has a lot of names. We can call it the gradient, or we can call it rate of change, and so on, or the slope, and so on. This is also called as the first derivative. So first principles is nothing but the same gradient formula with slightly different set of notations. The only difference is that when we make the increment in x, the increment is so small so that it is almost equal to 0. And there you go. That's how you derive the formula for the first principle. Hope you enjoyed the video. See you in the next one.